Okay, so we are going to talk about fluid resistance. Why do I put this here instead of where normal textbooks put them? The reason why I put them here is because I think the resistance is caused by fluids themselves, and like gases and liquids. And so I think introducing fluids before introducing fluid resistance makes sense in my brain. Most textbooks do projectile motion and the projectile motion drag alongside it. They will do like a drop ball and then the drag alongside it. Then most students think that that concept goes with the fact that there is a projectile. That's not true. When you think about what causes the drag or the friction or all of those things, it's actually the fluid resistance that causes the drag. If you were to take air out of the picture, a feather and a bowling ball will fall. What is the difference between the two? It's the fact that they are going through a fluid, right? And the fluid is causing the drag that's on it. Make sense? Okay, so now how do those equations change? When I write Newton's laws for resistance, what do I do? So imagine this is my Newton's law. What are the forces acting on an object? There could be a force that you apply, and then there is a force that's caused by the presence of a fluid. A fluid could be air, a fluid could be water, and it is always a resistive force. Just like friction, it resists the motion of whatever is going through it. So in general, this is what you will see. An applied force minus a drag. Or sometimes in textbooks, it will be written like this. F applied plus drag, but then they will use this and put a negative sign on the drag itself. I tend to use this scenario, but in my scenario, I will not put a minus BV. Actually, this should be a dot. Sorry, I forgot the dot. So you'll see it as a minus BV. So your drag force is a function of velocity. What does that mean? The faster you go, the more drag you experience. Right? Good. So I tend to, again, it's your choice how you want to do this, but I tend to put this as Bx dot. So don't double dip. Does that make sense? If you have a minus, it's like acceleration due to gravity. You can either call it a negative 9.8 or you just use the vector minus g and just call it 9.8. You do not do it twice, right? You don't call it minus 9.8 and you also put in a minus outside. So another thing that you will see sometimes is on the right side, what you will experience is they will write this equation as F applied minus D, which is the drag force. And this drag force could either be a function of V. So I could write this as drag is either a function of V, or this drag could be a function of V squared. And I'll give you an example. So think about water flowing down a pipe. If the flow is steady laminar flow, then the drag something experiences in it is a function of velocity only. On the other hand, if it's like a turbulent flow, going everywhere, the drag that object experiences in a turbulent sort of flow is a function of V squared. Okay? So this side of that equation can either be m dv over dt, or sometimes you will see it as m dv over dx. Do we all understand how that works? Yes? We've seen these before. Okay. So together, these two scenarios can be written as you'll see this here. Why? Because first is a function of v and the second is a function of v squared. Note, I am now using a minus sign here because I did not use a minus sign with the force outside. I just want you to be aware that that's what textbooks do. So if you ever see it, you won't get confused. Why did I not put a v squared there? Like here. I did not put a v squared here. This is v squared here, right? The reason why I didn't put a v squared is because I absolutely want to guarantee the fact that their minus sign will pop up. So now it will be directionally independent. So the drag acts whether you're going in the plus x or the minus x, right? So if you're going in the minus x, there will be a minus, and then total will become a plus. So you want to make sure that there is a minus, which is independent of the direction of the velocity. So B, C1, C2, they are all constants which depend on the thing that's moving through the fluid. So B, C1, or C2 are constants that depend on the geometry of the substance that's moving through the fluid. And in general, we talk about spheres. So in spheres, C1 and C2 could have these particular values. So for spheres in air. Now, again, this is very interesting to note. There is not a one value I can give you for friction. There is not one value of mu I can come up with. Why? Because mu depends on the two surfaces that are in contact. So that means for every two surfaces that are in contact, mu will change. The same thing with drag. Every single object will have a different value for C1 and C2. In general, for spheres in air, C1 is 1.55 times 10 to the minus 4 d. And C2 is 0.22 d squared, where d is the diameter of the sphere you're talking about. So if this is your sphere, this is your diameter. And again, remember, this will depend on what kind of an object you're talking about. Are you going through air? Are you going through water? Are you going through honey? How fast are you going? And that's an interesting question, because the faster you go, the change in the resistive forces changes. So I'll give you an example. So imagine for baseballs. Let's look for baseballs with a diameter of about 7 centimeters. The quadratic term dominates. For speeds greater than 0.01 meters per second. However, the linear term dominates for speeds less than 0.01 meters per second. So again, it depends on the situation that's given. Cars too. For speeds that are greater, remember I told you like the turbulent flow? So it becomes turbulent as soon as you start going faster. So like to us, it looks like steady, right? There's no air in it. But the faster you go, the more turbulence you experience. So then it depends on the situation yourself.